Hi, everybody. So welcome to a special presentation filled with lasers and kittens and mouse UFOs, along with machine learning and Python programming, of course. And I'm glad some kids can join us too. So I'm a PhD candidate at North Carolina State University. And my classmate, Maria Yaha, and my advisor, Dr. Laber, were also in this project. And Dr. Laber coded the base of the video game in Pygame, and Maria Yahya made various code improvements and graphic improvements. And I was mainly responsible for building the artificial intelligence part. Just a little warning. So here's the roadmap of the talk. First, I will give you guys a motivation of why we care about these projects. Now I will introduce the game mechanics of LaserCat. And then comes to the important part when we start building the AIs. So we'll start with the easy one, the imitation AI, which will imitate a human player's behavior. We will see how we can formulate and solve it as a supervised learning problem. Then we'll get to the more exciting part where we build a self-evolving AI, which uses reinforcement learning. And we will see that it is quite different from supervised learning. And in the end, we'll have an epic finale, but I don't want to spoil it just yet. Okay, so why do we care at all about doing projects on a video game? Well, besides the obvious reason that it's cool. So video games are actually a great testbed for various machine learning algorithms. They are designed to be beatable, but also difficult enough to give the player a challenge. So it is a great testbed for you to try and improve your algorithms. So for example, DeepMind from Google wrote a paper about trying their reinforcement learning algorithms on various Atari games. And then more recently, we know that AlphaGo was able to beat human professional Go player. And then thirdly, many real-world problems can be formulated as a sequential decision-making problem, similar to a video game. So in a video game, you look at the screen, and then you decide which action you want to take. So problems like self-driving vehicles, you see what's in front of you, and then you pick the right decision to make. Or personalized medicine, where you observe the patient's historical status, and then pick the best treatment for the patient. Or counterterrorism, where you know that the terrorism are on the run, but you have limited resources from the police department. What's the best strategy to allocate your resources to catch the terrorists? So all these problems can be formulated as a sequential decision-making problems, and then you can solve them just like video games. So here's a demo of what a game looks like. You are controlling this cat here, and you shoot lasers at the mouse UFOs. And you can move in 8 directions. In each direction, you can either take a small step or a big step. A big step allows you to move faster, but you also lose precision. You get points for shooting the UFOs. You lose points for colliding with them or letting them escape. And the catch is, the closer you are to the left boundary, the more points you get for killing the UFOs. So it's a high-risk, high-reward system. As mentioned, the game is built with Pygame. It's a library in Python, and there are a lot of great tutorials online to teach you how to make video games. But the focus of this talk will be on the AI portion, not the game-making portion. And there are 3 key functions that allow you to build an AI. First, you need to be able to extract information from the current state of the game. And then secondly, you want to map that information to the desired action. And then you want to be able to pass the action back to the agent to let it execute it in the video game. The first and the third steps are relatively straightforward. They come down to knowing the correct syntax, which you can learn from the tutorials. And we are going to focus on the second part, which is going to be the brain of the AI. So let's start with imitation learning. And then in this part, the AI is going to try to imitate a human player's behavior. So the data is generated by the human player. And we can formulate it as a supervised learning problem, where the predictors will be the coordinates of each object on the screen. The lasers, the small UFOs, the big UFOs, the cat, etc. And then the response, which is the correct answer, is the action that the human player took. So this will be a screenshot, and we have these various objects. We will just extract their coordinates and use them as the features or predictors, and then try to let the agent imitate a human's behavior. But the catch is, not everything is on the screen. So maybe you kill some UFOs, so there's only one UFO on the screen. But maybe when you miss, there'll be 2 or 3 or 4 UFOs on the screen. And then sometimes there's 1 laser on the screen, sometimes there are 3 lasers on the screen. So there are a lot of missing values. And these missing values are a little bit special, different from normal missing values, in which case the missing values exist, but we just fail to measure them. So you can use the various methods to impute these missing values. But here, if the 3rd and the 4th mouse are missing, it's not because we couldn't measure them, it's because they are not there. So it doesn't make sense to impute them. This is called a structural missingness. So how can we handle this structural missingness pattern? We'll build something called a hierarchical random forest model. So first, we look at the data, and then we divide the data into different categories based on the missing value patterns. So maybe category 1 is no mouse, no laser, just a cat. Category 2 will be 1 laser, no mouse, just a cat. And category 3 will be 1 laser, 1 mouse, and so on. So after we divide the data into different categories, within each category, there's no missing value anymore because they all have the equal number of inputs. And after dividing the data into different subcategories, we build a separate model for each category, and we don't have the missing value problem. And here you can use your favorite classifier. We use the random forest, but you can also use support vector machine or artificial neural networks. And then in Python, you can just use the scikit-learn library, where it gives you a huge variety of machine learning algorithms. So we are ready to see how the AI does. On the top will be the human gameplay, and on the bottom is the gameplay from a hierarchical random forest AI. And it's important to note that this is the test data. So these data are not part of the training, and this is test data. And so here, the AI is trying to predict what I would have done in this scenario. And on the top is that I replay the game using the same seed, basically, to make a comparison. So not too bad. And this AI is actually only using 2 hours of gameplay. So actually, with more data, it can do even better. But I was going insane from playing hours of LaserCat. So I just had to stop there. All right. So from Terminator to Skynet, what you just saw, imitation learning AI, is in essence deterministic. It's trying to imitate a human's behavior. So it's deterministic, and it cannot evolve on its own. But a true AI should be able to learn and evolve on its own without a teacher. It should be able to get smarter and smarter and eventually surpass human intelligence, and hopefully they're still our friends at that point. So in other words, we want to move from Terminator to Skynet, and we will see how we can actually build a Skynet. To do that, we use a different algorithm. It's called reinforcement learning. So here you have an agent, which is the learner and a decision maker. It will observe the current state of the environment, which is what the agent interacts with. It observes the current state, and it will try to pick an action. And then in turn, the action is going to influence the environment and make it move to the next state. The environment will also provide the agent a feedback. It's called a reward. It quantifies the desirability. And then a policy is a map from the observed state to the action. And the policy itself, the policy can evolve over time. So typically, the agent starts from knowing nothing. So it will be a random, completely random policy, a random walk policy. And over time, you want to be able to use the reward as the feedback to let the policy converge to an optimal policy. So this concept actually comes from animal psychology. So if you train dogs, when it does the right move, you give a treat. And the same thing for humans. So the first time you eat ice cream, you really like it. So in the future, you know that eating ice cream is the correct action, so you want to do the action more. Or if you accidentally eat a chili pepper and you burn your lips off, next time you know you want to avoid chili peppers. So the concept comes from human psychology, and our agent is going to explore by trial and error and try to learn the optimal policy. Now, this is different from supervised learning. In supervised learning, instead of a reward signal, you just get a correct label. So you know what the right answer should be. But a reward is slightly different. It could be negative, or it could be positive, and it can be continuous. So even when it's positive, you don't know for sure if it means that your action is correct, because maybe there's a different action will give you a bigger reward, and that will be the better action to take. And the other thing is the reward can be delayed. So the right action might give you a positive immediate reward, but in the long run, it might give you a negative reward. So for example, you like eating ice cream. So eating every ice cream will give you a positive reward. But you keep eating it, and a couple hours later, you get stomachache. So that's a big negative reward. So the actions that you overeat ice cream is actually incorrect, but you wouldn't find out immediately. So the reward is a weaker signal than the correct labels. And that's why reinforcement learning is also called semi-supervised learning. So we can look at these concepts in LaserCat. The agent is going to be the cat, or the AI that controls the cat. And then everything surrounds it is the environment which the cat is going to interact with. And then the cat will take an action, and then the environment will move to the next state. And here we can see, as I mentioned, the reward can be delayed because for the cat moves to this position, it is the correct action, but the laser hasn't reached the mouse yet. So the immediate reward of this action is actually 0. And when the laser kills the mouse and you get a positive reward, the cat might be doing something completely irrelevant. So the tricky thing is, how do we assign the correct actions, the credits? The other challenge is the sparsity of rewards. The game actually runs at 50 frame rates per second, so you have 50 states per second, and you only get a reward signal in a very small proportion of the states, so it's a very sparse and weak signal. And the third thing is, we want to be able to handle the exploration versus exploitation trade-off. As I mentioned, if you want to find out the good policies, you have to explore. But once you have some good candidate policies, do you just use the currently best policy to get as many rewards as possible, or do you keep exploring and potentially get really negative rewards? It's like you want to try different restaurants. Do you go to your favorite restaurant and order your favorite dishes? Or do you try a new restaurant, which could become your new favorite, or it could be completely disastrous? And usually there are just too many scenarios. There could be too many restaurants and too many dishes for you to try exhaustively. So how do you decide that the current policy is good enough? So these tricky things will be answered by the subsequent slides. And as I mentioned, the short-term reward could be misleading. If we just focus on short-term reward, in the long run, you might get into really bad situations. So instead of looking at the reward, we want to look at something more meaningful. It's called the value of a state. So basically, the value of a state is the expected cumulative long-term reward from following a certain policy, starting from the current state. It's going to be the sum where RT is the immediate reward plus a discount factor times the reward of the next state plus a discount factor squared times the reward of the next state, and so on. So it's a long-term cumulative reward. But we need this, and this discount factor is going to determine how much weight you put into future rewards compared to the more recent rewards. If gamma is close to 1, then you care more about the future rewards. If gamma is 0, then the value of a state reduces to the immediate reward. So gamma is the trade-off between long-term and the short-term rewards. And if we look at this summation, we can leave the immediate reward here, and we can group the remaining terms over here, and we pull out a gamma. And then we find out that within the bracket is actually the expression of the value of the next state. And it is actually quite intuitive. This is saying the value of the current state is equal to the immediate reward plus a discount factor times the value of the next state. So we care about the immediate reward, but we also care about how promising the future state is. So this equation in theory should hold, but in practice, when these are all estimates, the equation is not going to hold. And actually, the right-hand side will carry more information than the left-hand side because the immediate reward is observed. So the right-hand side carries more information, and that will actually give us the updating algorithm. We start by randomly initializing the values. We had st and we had st plus 1. And then because the right-hand side carries more information, we let the current estimate take a small step towards the right-hand side. So this is a convex combination of the current left-hand side and the right-hand side. And this carries more information. We take a small step towards the right-hand side. And alpha is the learning rate. You might ask, why don't we just let alpha equals to 1 and just use the right-hand side to completely replace the left-hand side? Because here, the RT is actually the expected reward. And in practice, the reward itself can be a random variable. So if we just let alpha be too big, your estimates can just move or shift around if the reward is random. But just knowing the value of a state might not be enough, because maybe you know that some state has a really high value, but if you don't know how the game works, if you don't know the mechanics of the game, you don't know which action you're supposed to take. Here we know because we wrote the game, but if you face a new problem, even though you know a state is desirable, if you don't know how to get there, then it's pointless in terms of how to choose your actions. Which is why we just make a small modification. Instead of looking at the value of a state, we look at the value of a state action pair. So QSTAT, which is the value of a state action pair, is the expected cumulative long-term reward from executing action AT at ST and following pi afterwards. So the only difference here is that this denotes the value of executing action AT. And then suppose we know that the Q function of an optimum policy, Q star, is known, then it is straightforward to choose the best action. We just choose the action that gives us the maximum expected long-term reward. So if Q star is known, choosing the action is straightforward. It's the maximizer. Now, recall the equation from before. It's actually called the Bellman equation. The long-term reward of current state is equal to immediate reward plus discount factor times the long-term reward of the next state. And very similarly, the Q function has a similar equation. We have the long-term reward under optimum policy of a state action pair equal to the immediate reward plus discount factor times the maximum of the Q value of the next state. Here we have this maximum because we know the best action is the maximizer. So the optimum policy is going to follow this equation, and similar to before, we can use this equation to have the update algorithm. So although these equations maybe take some time to digest, we can see that programming-wise, it is almost trivial. So that's the good part. And then going back to the exploration versus exploitation policy, when you want to explore, usually the typical policy you choose is called the epsilon greedy policy, when you have a small probability to explore a random action, and you have a large probability to pick the current best action. And then you can decide how you can tune the probability parameter to decide how much you want to explore and how much you want to exploit. In essence, this algorithm actually allows you to get the optimal policy no matter what exploration policy you choose. So you can just use random walk policy, but sometimes there will be stability issues. And in LaserCat, the actual algorithm implemented is called Bayesian Q-learning. It's a variation of the Q-learning algorithm. Because my brain usually shuts down upon hearing the word Bayesian. So we won't go into that today. I don't want that to happen to you in this short talk. But if you're curious, on a very high level, we are still going to use the right-hand side to update the left-hand side. But instead of updating the point estimate, we put a prior distribution on the left-hand side, and we use the right-hand side as a sample to update the posterior distribution. But you might recall, so all this sounds really good, but notice that they are dealing with the state is the input. So what happens if the states are continuous, like in a video game? It's continuous, and there are just so many states. How can you possibly find the Q values of each state action pair? There are simply too many states. And if it's truly continuous, there are infinitely many states. So we have to somehow handle the continuous states or large states problem. And one strategy is to use a parametric function approximation, where instead of assigning a Q value to every state action pair, you use a parametric function to approximate the state. It can be deep learning, or splines, or radial basis functions. Or the other way, which is the more straightforward way, is called segmentation. We simply discretize the continuous states and then make them into discrete states. Examples include tile coding or nearest neighbors. And so if you look at a typical reinforcement learning problem, it's called a mountain car. When you try to drive the car to the goal position, but you have to back away a little bit and then gain enough momentum to drive all the way to the right. And so this is a continuous state. And we can simply lay out a bunch of grids on top of the state. And now we can use these grids to track the approximate position of the mountain car. And then for each small grid, we can assign it a Q value for each action. So in this way, we turn our continuous states into discrete states, and we can do everything just like before. Now, the tricky thing about LaserCat is here we only need to track one car, the mountain car. But in LaserCat, we have a cat, big UFO, small UFO, and the lasers. We have so many objects to track. And if we try to build grids for each object, and now we have to still consider the interactions of them to truly discretize the states. And that will simply be too many states. So we have to improvise a little bit and do something, we can call it the mobile tile coding. So instead of laying a stationary grid for each object and try to track them all and consider the interactions, we notice that we can play this game greedily by just letting the cat try to shoot the first mouse. And then we can simply build a grid which centers at the mouse and then moves with the mouse. So the grid is no longer stationary. It moves with the mouse, and it tracks the relative position of the cat with respect to the mouse. So now we only need one grid to solve this problem. I guess a small detail is that, so how big should this grid be? This grid actually needs to be 4 times the screen size, not just one screen size, because the cat can be in all 4 quadrants with respect to the mouse. So like a worst case can be the mouse is on the left corner, cat is on the right corner, or mouse is on the top left corner, cat is on the top, bottom right corner. So we need this grid to be 4 times the screen size. And then you can just do like integer division or something to just round down and get the approximate coordinates of the cat. And then you can label them and then treat them as discrete states. So now we know how to update the Q values, and we know how to turn LaserCat into a discrete reinforcement learning problem. And that's actually all we need to know to build a self-evolving AI in LaserCat. Don't tell Peter. Okay, so let's do a small recap. And here, we start with the motivation behind the projects of video games. As I said, life is a game. Many real-life problems can be formulated as a sequential decision-making problem, and we can solve them as video games. And now we learned how to build imitation learning AI, where we can use the coordinates or just various features you can construct from the current state of the game as features, and then the human player's action as the correct answer, and we can build a predictive model. And we use the hierarchical model structure to handle the missing data problem. And now we learn how to build a self-evolving AI. It's the reinforcement learning algorithm allows the AI to explore and learn the best policy by trial and error. And then we learned that value functions are the long-term cumulative reward of a state, and it is more informative compared to the immediate reward. And if you don't know the mechanics of the game, you can use Q-learning instead of estimating the value function to know what the best action should be without knowing the mechanics of the game. And then lastly, we see how we can use segmentation method to turn a continuous state into a discrete states. And I'd like to point out that the devils are always in the details. So although the algorithms seem relatively straightforward, usually they are just a huge variety of algorithms, and then some of them work in your case, some of them don't. And when they don't work, sometimes it can just be because you missed one hyperparameter or because the problem is innately not possible for the algorithm. So finding out what works and what doesn't work is the most painful and the hardest part. And before I take questions, I'd like to share my contact information. So you can get this video game LaserCat on the website of my research group for just $12.99. But yeah, actually, you can play it for free. And here's my email, and I'll take questions.
All right.
Please.
Thank you for that. That was an awesome presentation.
Thanks.
I was curious about the policy in terms of, since the self-learning AI actually iterates to get to the optimal policy, is there any investigation of what was actually derived at the end? Like, is there a feedback loop for a human then to analyze that policy that was optimized and gain some new insight into how to play the game better
Yes.
themselves?
Yes.
So could you comment?
Yeah, so you can see how the AI works. So see that recall that the Q value is a function of the state and the action, and the state itself. And if the states are continuous, we can approximate this Q value with a parametric function. So it can be deep learning, or just in the simple case, we can consider it to be a linear approximation. So say the Q function is a linear combination of the coordinates of the objects. And then as the AI plays, it's going to try to find out what the correct parameters in the linear combinations are. So you will know, like, given the current coordinates of all the objects, what values correspond to which action. And once you know what the Q values are, you know what the best action will be. So think of the learning process as learning the correct parameters for the estimates of the optimum Q value. So in that sense, in the end, you can see what the correct parameters will be.
What is a video game?
Okay. What is a video game? A video game is a sequential decision-making problem, which is the most important problem in the world, and you're gonna grow up and become a statistician.
As the environment becomes more and more complex, how well does this hold? You know, if you had more actions, a 3D environment.
So it's the curse of dimensionality, right, which is present in all the video games. So usually when the environment is more complicated, the simple methods won't work. Like even tile coding could just be insufficient when your environment is huge. So which is why recently deep learning is gaining a lot of popularity when they would just use a deep neural network to do the function approximation. So here we are still cheating a little bit by extracting the coordinates of the objects. But you can imagine in real life, we can't extract the coordinates. We can only observe the screen. So now the 2D image becomes the input. But you can use a neural network to use that as input, like a convolutional neural network, and you can use the image itself as the input to build your Q function. But now, of course, that still relies on more complicated algorithm and more computing power.
So I know you said you didn't want to talk about it, but why be Bayesian?
So the Bayesian algorithm, like the key difference between the Bayesian and the classical Q learning is that in the classical Q learning, usually the exploration policy is epsilon greedy, as I mentioned. With a high probability, you choose the current best action. With a small probability, you randomly explore all the unknown actions. But Bayesian Q learning, the nice thing about it is that it's doing a more educated exploration because you'll be updating the distributions of the Q functions. And then when you pick the action, you're actually sampling from the distributions. So say, if an action hasn't been explored before, its prior distribution has a high variance. So when you sample it, there's a high probability that it becomes the largest value and you can sample it. So you get to explore it. And then the several competing actions, they maybe have very similar distributions, but their distributions will give you higher means than the worst actions. So you end up exploring those actions more. But in short, in Bayesian Q learning, you end up exploring the more competitive, the several top candidates more often than the remaining actions. Whereas in classical Q learning, you explore all the actions randomly. No, that's the key part, right? We don't want to use prior knowledge. We don't want to use domain knowledge. We want to let the AI figure out itself. So in the Bayesian Q learning, we put a non-informative prior to all the Q values. So it can be a normal distribution with a very, very large variance, or it can just be a uniform distribution.
So does that perform better though than maximum likelihood? I guess I'm just like yeah, does that actually, did you test just a pure maximum likelihood? Because I guess like when I think of Bayesian methods, I think it's like it allows you to more efficiently learn something about your data when you have some, you have good prior knowledge, basically.
But yeah, as I mentioned, in this case, you actually don't need prior knowledge. And this algorithm really just try to give you a way to explore the top candidates in a more educated fashion. But you bring back the question, well, is it always going to be better than like a classical Q-learning or other methods? In this case, it performed better, but there's no golden method that works for all the cases. So usually these algorithms are very case dependent.
So you mentioned about how you actually got dimensionality reduction by modeling the relative position in space, but you didn't actually mention how you got around the curse of dimensionality for the number of targets, right? So you talked about training on one target, and that's a
Yes.
simple problem, but your state space also is exponential in the number of targets. So how did you guys deal with that?
Yes, yeah, that's a good question. I mentioned briefly. So we noticed that in LaserCat we can play greedily by just shooting the first mouse. So in this case, we only focus on the first target, and we train cat in that fashion. Let it only focus on the first target. So in this case, solve the problem. But of course, you can argue that it's cheating a little bit because we are giving it a little bit prior information.
Hey, I'm curious about under current settings, how long does your algorithm, how long does it take to converge? And did you face any instability issues? Yeah.
I faced instability issues a lot when I tried a bunch of other algorithms. But luckily, in this case, Bayesian Q-learning converged. So technically, so it depends on exploration policy. If you have a fixed exploration policy and you're simply trying to learn the value associated with that policy, there's convergence guarantee. But if you're exploring with a policy and you're trying to estimate the values of a different policy, say the optimum policy, typically there's no convergence guarantee and you have to check the results empirically. And in this case, as we see in the video, after an hour and a half, the AI is already performing pretty well. And in 7 hours, it pretty much achieves the optimum performance. And it's running at 50 states per second. So it is still a large amount of data. But then, computing-wise, in this case, it's not that heavy. If we don't blitz everything onto the screen and we do parallel computation, it can even be faster time-wise.
Hi. So my question was, if you ran this algorithm multiple times, do you believe that different strategies would emerge, using different priors? Or if, say, you handicapped the AI for some reason, do you think that it would learn differently on different types of training?
Yeah, so the strategies will, the parameters will definitely impact the strategy. And for example, the discount factor. If we set it to 0, your agent is going to try to only focus on the immediate reward. If we let it to be big, and it's going to take into account of the more future rewards. And the reward itself also plays a factor. Right? We are penalizing the cat for running into the mouse, but if we don't penalize that, then the cat is not going to care about running into the mouse, and it will just try to kill them. So the parameters will influence the behavior of your agent. And even when the parameters are fixed, that could be multiple optimum policies, as long as they give you the equal number of values. So maybe you can consider when you play a chess, maybe moving left and moving right will both give you a checkmate. And in that case, moving left and moving right are both the correct action. They are both optimum policies.
Let's thank our speaker for keeping us safe from space rats.
Thank you very much.